Hello, my name is Pol del Aguila, and I'm a research staff scientist in the CIBM Center for Biomedical Imaging and a postdoctoral researcher at the EPFL Biomedical Imaging Group. And I'm here today to talk about this paper, accepted to ICASSP 2022, about bona fide risk projections for density estimation. So this is basically using generalized sampling from signal processing for density estimation and how to do it so that the resulting estimates are bona fide, so non-negative and integrating to one. Let's begin. So first off, this is part of an effort to use the power of regular grid spline interpolation, which is a major point of expertise here in the biomedical imaging group for density estimation. So for those of you who haven't thought about the problem of density estimation before, here is a pointless rendering of the conference backdrop where this is for you to change the perspective of thinking, for example, of images as pixels where the value is corresponding to the intensity, and see it more as it would be in density estimation, in which simply it's a set of a cloud of points where the density of the points in each place depends on how dark the image initially was there. So moving on, I'll review a bit the theory of generalized sampling or the approximation in shift invariance function spaces. So it all starts from supposing that we have a finite energy function and we want to represent it somehow. And this representation should be discrete, so either finite or countable. We want to be able to store it. We want good approximation properties, of course. We would like the approximation to represent the function closely. And we would like some sort of shift invariance. If there's a pattern here in one piece of the function and a pattern there, we would like to have some kind of guarantee that they will be represented in the same way or with the same accuracy. So what people use typically in this context, or the theory of generalized sampling, is to use shift invariant spaces in which a function is represented as a weighted sum of basis functions. And these basis functions are simply a shift of one another. So here, an example portraying what I'm saying is that the blue curve is composed of shifts of this gray curve multiplied by different weights. And that's how we construct a representation of a given function, f tilde. So this has a discrete representation because there are the coefficients. It has good approximation functions as long as the basis functions we choose follow the risk basis condition. And it has some sort of shift invariant in the sense that if we shift everything by an integer, nothing changes, just the coefficient shift by an integer too. And the error order, so how small the order gets as we get a better and better discretization, is controlled by our choice of basis function. So how do we find these coefficients? Basically, if we want the best approximation in this space Vs, the theory tells us that there's a certain called dual basis function that follows this p-orthonormality property. That just taking inner products with that function of the function we want to approximate with that basis function will give us the right coefficient. So the good news is that we do not need to find this function in practice, and now you'll understand why I say that. So let's see this a bit in the context of signal processing, in which we're used to seeing sampling as, okay, we have a continuous domain thing f. We pass it through a linear time invariant system characterized by a function impulse response g, and then we sample the result. So this is actually the same as we've been talking, because it turns out that this is equivalent to taking a product of this function f with some analysis function that is simply the mirrored version of the impulse response. And so the ideal case in the context of what we were discussing is that simply, okay, this analysis basis function is simply the dual of the synthesis function, and then we're done because we're already obtaining the coefficients that we wanted. So this happens, for example, in the case of simply a rectangular function as basis function. So step constant, or piecewise constant representations. in more practical cases, what we hope for is that even if the basis functions are not the same, we hope that the span of the analysis function and the synthesis function is the same. And in that case, we have a very nice property, which is that this dual function that we talked about before can be expressed in terms of coefficients Q of K of the analysis function. And that means that actually we can get the best coefficients as discussed before by simply convolving the measurements with some digital filter Q. In order to know which digital filter Q, we use the consistency principle. So basically that if we were to measure our own representation of the function, we would like to get the same measurements that we got in practice. So by doing that, it's very clear, very direct to see that this Q has to be the convolutional inverse of the correlation between the analysis and synthesis functions. So as a result, if we do this simple digital filtering, we will obtain the orthogonal projection of the function f onto PS. So the whole motivation behind this project is why don't we do the same, but for density estimation? So we replace the function we wanted to approximate f by simply a train of deltas at the spot where we got samples. This is called the empirical estimate for the samples that we got. And it looks like that. So if we do the exact same procedure I described, and we choose as synthesis and analysis functions, simply the rectangular function shifted, we get the standard histogram. So what happens if we increase, like the rectangular function can be seen as a B-spline of degree 0. So what happens if we increase the degree of that B-spline? Well, we get a better approximation. It's piecewise linear instead of piecewise constant, and it looks good. We further increase it, but we then start to notice a problem. There are some points in which our approximation is negative, which is against the rules of probability density functions, as we all know. Will it improve if we further increase the degree? No, it actually gets worse. The approximation in terms of error, as you will see soon, gets better, but there are more and more incidents of this kind in which we violate the non-negativity constraint on densities. So before getting to the point of how we solve this, which is the objective of our paper, let's see a bit the error characteristics for this approach to density estimation. So in this paper in ICASSP 2004, they defined this metric, which is basically the L2 error, but it's averaged over possible shifts in the grid, because that's something no one can control. We don't know which shift in the data and which shifts in our grid we will have. So it's an inherent problem. And we introduced this parameter H, which is simply the space between two consecutive nodes on the grid, because before we assumed it was one for simplicity of the expressions on the slides, but now we analyze it in terms of this H. So it turns out that then you can get those forms expressions for this error metric, and the result of both the theoretical expressions and an empirical analysis of simply estimating a standard Gaussian from 1,000 samples is that there is a compromise in the choice of this space in the grid, like this discretization step H, in which it's controlled to the left, where we basically are choosing very, very small discretization steps. It's controlled by error coming from statistical error, because basically the bins or the discretization steps get so thinner that there are less and less samples in each of them, and then the variance gets in. And to the right by the approximation error, that simply if you choose an H that is wider than the changes you want to represent in your PDF, then you commit errors there. So it's a nice theory. Now, let's see how we improve on that. We said our problem is mainly non-negativity. Non-negativity is a problem that mathematically is well conditioned because like this space of functions we can represent using our synthesis functions, but that are non-negative is a closed convex cone in the whole space and in L2. So that means that there is a unique projection of any f that is the best non-negative function in VS to approximate. But it's an open problem how to find it, how to obtain it in a practical way. So what do we do there? Well, let's consider, besides non-negativity, let's consider also integration to one. So these two properties together are known as bona fide PDF, because basically it's the rules that PDFs have to fulfill. And incidentally, like the approach we've presented up till now fulfills the second condition, so the estimate to always integrate to one, but this loses part of its meaning because since they're not non-negative everywhere, integration to one is not such a big deal anymore. So what we propose in our paper is to take this consistency principle that we had, so that basically if we measured our reconstruction or representation, we would get the same measurement as we initially got, and relax it a bit. So make it not a constraint, but an objective, and then constrain that cost function on the bona fide properties. So of course, here again, we have the problem that we do not know how to impose non-negativity everywhere. But what we do instead is impose it in many places. So basically, we choose a parameter hc that it's smaller than h. So at many points in between any 2 points in the regular grid, we impose that the function is non-negative, and it still integrates to one. And this problem we can actually solve quite easily, because the first term in the objective function is simply the measurements. The second term is the coefficients we're looking for convolved by the correlation between analysis and synthesis function. And the constraints can be expressed with a simple convolution of these synthesis coefficients upsampled by a factor of m. This factor m is the ratio between h and hc. And we simply need to sample the basis functions also more thinly. And then basically we can solve this problem because it's convex, it's quadratic cost function, there are linear constraints. And of course, in the case of density estimation, we will always have a finite amount of delta. So everything will be finite to port, and therefore the problem will be finite dimensional. So in terms of error characteristics, we see that it actually improves about 1 dB beyond what the pretty good estimates, but not bona fide estimates we had before. But most importantly, here in an example, we see that not only the resulting estimate fulfills the conditions of not crossing the zero boundary, but also its behavior around high frequency areas of the PDF is substantially better. So this accounts for the error improvement of 1 dB or so. So that's all for today. So I'll end by thanking the biomedical imaging group in general and the CIBM, but also Dr. Aleix Boquet-Pujadas, who was in intensive discussions around all of these topics, and specifically on the non-negative projection in spline spaces.